So I'm Julius, one of the co-founders of the open source Prometheus monitoring system. I'm also founder of PromLabs. PromLabs is just a one-person company. It's just myself kind of over the years trying out different, services, trainings, products, and so on around Prometheus. All right, so today I want to talk about a number of best practices and pitfalls when you're using the Prometheus monitoring system. This talk will be useful for you if you are already using Prometheus somewhat. I think if you've never touched Prometheus at all, there might be a lot of things that I'm mentioning that will be like confusing, terms that are used that you have to know already. So in that case, I apologize. All right, so let's start with a little story here. So I don't know who knows the actual Greek myth of Prometheus, the Titan who stole fire from the gods and brought it to the humans, brought illumination to the humans, right? It's the great thing about Prometheus, but the gods didn't like that too much. And they tied him to a stone for all of eternity. An eagle would come every day, eat Prometheus's liver, and then the liver would regrow, and the next day the eagle would come again and eat that liver. So that's the sad ending of the story, and there's some variance to the myth. But with the Prometheus monitoring project, it's sometimes similar. Sometimes it's quite nice, it works well. It's like in the first picture, and sometimes it's a bit of a pain. And the goal of this talk is to make you feel a bit more like in the first picture. So I'm going to cover best practices in a number of areas of Prometheus: instrumentation, like getting metrics out of the things you care about. Then how do you define alerting rules on top of that? How do you write PromQL queries in general, like some best practices there? And then monitoring topology, how do you plug together parts of your monitoring in the best ways? Let's talk about instrumentation first. So first, something very general, not really Prometheus specific, but Prometheus does allow you to add a lot of custom metrics to your application code. So a question that comes up immediately is, what metrics should I even add to my applications? And there's some well-known guidelines around this. If what you are adding metrics to looks a bit like a resource, like a CPU, disk, a queue, things that can be full or empty, that have a certain utilization, saturation, things waiting for things. Then the use method is one handy guideline for what types of metrics to add to such a system. You can find more details about that on this link by Brendan Gregg, who actually, I think, invented the term. If what you are monitoring looks more like a request-serving system, like a web server, database server, or so on, then the red method is a good alternative, tracking requests that are happening, errors that are happening to those requests, and then also checking, what is the distribution of latencies of the handling of those requests, with histograms, quantiles, and these kind of things. In general, with Prometheus, it has this hugely dimensional data model, but metric names that don't split up aspects by further labels, they're actually really cheap. They produce a single time series out of a given server. So spread them as liberally as possible in your application code. Everywhere where you would have had a log line that some error has occurred, I would recommend you to just put a counter metric there, counting and incrementing that this type of error has occurred. Could be useful later on. It doesn't cost much. Also, don't instrument just your applications themselves, but also your shared libraries that multiple of your applications use. So, if you have an RPC library or so, you could directly put instrumentation in there, and then from your application, using that library, just pass in a Prometheus metrics register object, and then all those nice RPC calls will automatically get metrics as well. Okay, let's get a bit more Prometheus specific. If you've used Prometheus, we have this metric name concept, which is part of a time series name describing the aspect of a system you are monitoring. And it's really just a string. And while there's some parts of the system that have a bit of an idea of the meaning and the type of a metric name, whether it's a counter, gauge, summary, histogram, that doesn't really make it into the TSDB and not fully into PromQL. So the Prometheus server in most places does not have a way to statically enforce whether you are using a metric correctly, semantically, from the unit perspective, whether it's a counter or gauge or so. So the next best thing we can do as humans is to follow a number of conventions. We've written them down in the Prometheus IO docs, but just some of the most important parts here. If it's applicable, put a suffix of the actual unit into the metric name. So bytes, seconds, whatever it is you are measuring. Use base units, so SI base units usually, seconds versus milliseconds, bytes versus megabytes. If you stay in those base units, things stay more easily comparable, especially if you do comparisons, arithmetics, and so on between different types of metrics. To make it clear to the human reader whether a metric is a gauge metric, a metric that can naturally go up or down, like the current count of something, versus a counter metric, a metric that is a cumulative count that can only go up over time. We also have this convention that you should add an underscore total suffix to manually created counter metrics to make it clear to the reader if it's a gauge or a counter. And then there's the question of sometimes what time series do I fit under one metric name with different sets of labels versus what do I split up in multiple metric names. And the rule of thumb there is that everything that you put into one metric name, it should make sense to either sum over all of those time series or to average over all of them. So for example, if you have a memory usage metric that splits up the usage of memory by system, user, and different types of memory usage, you should be able to sum with a sum aggregator over all these different types of units, of usages, and get a total usage. Okay, so another favorite beginner pitfall that Prometheus users fall into is cardinality bombs. So, in Prometheus we have these metric names, and then we have the awesome concepts of labels, key value pairs that allow you to partition your metric names into further, detailed subcategories, like what method you are tracking an HTTP request for. Here, I'm just doing it in a totally okay way. I'm splitting up by the HTTP method, tracking each one in a counter separately. Post, get, put, delete is just 4 different methods. Everything's fine. And now you have an overeager developer, like super happy, labels are awesome. Let's maybe also track what users actually, has executed that request. So they might get an idea. Hey, let's put a user ID as a label into all of my metrics. And those user IDs, if you have a big service, you might have millions of users or billions even. And not only does each user ID gets combined with every method, so it's kind of multiplicative, right? So you have 1 million users times 4 different methods. You have already 4 million time series now, because every unique set of labels creates one unique time series that the Prometheus server needs to index and track. So this goes boom really quickly. The number of time series that the Prometheus server currently has to track is one of the main scaling bottlenecks of a Prometheus server. And yeah, so boom or OOM out of memory. That is unfortunately something that can commonly happen. Someone taking photograph. Okay, you're done. Awesome. So keep that in mind. Try to not put these unbounded label values into certain labels, right? Like public IP addresses, user IDs, or full HTTP paths that can contain such IDs. At SoundCloud, initially, where we started Prometheus, accidentally, some people put full HTTP paths in a label value, and they contained a SoundCloud track ID, of which there are 100 million. So that didn't go well. Try to keep these label values, well bounded. Think of the multiplicative effect. What really matters, though, in the end, is the total budget you have in a typical large Prometheus server. So A large Prometheus server can typically handle up to a couple of million concurrently active time series that it's ingesting at one time. But then you also have to think about when you want to query these metrics, at least in the table view, you want to be able to comfortably query all the time series belonging to one metric name. So keeping all the time series within one metric name to normally a couple of hundreds, to sometimes thousands, and very rarely a couple of tens of thousands is probably a good idea. So choose your metrics, the labels on those metrics, and then the number of targets that expose these metrics accordingly to kind of in some way stay under these two budgets. When you create metrics to track successes and totals and failures of some operations that happen in your system, it might be, you might first think, okay, let's create a counter for all the failures that are happening and all the successes that are happening. But the most common operation you want to do in PromQL is to take a ratio of what's my error rate ratio, right? Like what's the percentage of errors I'm getting. And the PromQL expression you now have to write gets a bit complicated with these two types of counters. You have to take the rate of the failures, and then you actually want to divide by the total. But to get to the total, you have to then sum up the rates of the successes and the totals. So this all becomes easier if instead you track just the failures, the errors, and the totals, and not track the successes separately. Then it's a very simple ratio in the expression. Okay, another thing that can be quite confusing for users when you're instrumenting and building graphs or alerts on top of the metrics that you instrumented is when series are missing. So imagine you are instrumenting a server with a metric that tells you how many operations of a given type have happened so far. Maybe there's only 4 types: create, read, update, delete. The problem is that the instrumentation client library has no idea of what these 4 different types are before one of those operations actually happens, and you say, okay, increment this counter for the read operation, for example. So when you first start your server, Prometheus scrapes it, there will actually be no time series at all exposed for this metric. And that can make you run into some query trouble. Like if you build a graph wanting to show the total rate of operations, but no operation has happened yet, then this inner selector of ops total will return no time series at all, the rate will be empty, and then the sum aggregator around that empty rate will also give you an empty result. So instead of a 0-line graph, which you might expect, you would get an empty graph in Grafana. Similar, if you are selecting the rate of a specific type of event and that specific type has not happened yet since that instrumented server has started up, you will also not get any result at all. So this can break both your alerts and your dashboards. It can be a bit dangerous. So if feasible, if you really only have a certain number of already well-bounded, well-known label values, you can actually step through those when your program starts up, loop through the different known label values, and just reference that labeled metric once with each value to instantiate it internally in the client library without actually incrementing it. So I'm not adding a .inc at the very end of this call here. This is a Go example. This will really just tell the Go client library, create a default of 0 for this counter. And yeah, you don't have to worry about this for metrics which don't have any labels on them, because they automatically get initialized to 0 when the program starts. Sometimes this isn't really doable. Like if you have HTTP status codes, you don't want to pre-initialize one time series for all the different possible HTTP status codes. That would be a bit overkill. But you still run into the same problem. So either you have to be kind of aware of this and be fine with your graphs being a bit wonky and nothing has happened yet, or you could use the OR set operator to do a set union to join in like default values that are always present to show a 0, for example. There's more details in this link below here if you want to know how that works exactly. Finally, when you add time series to some server, process, host, machine, whatever that you care about, it can be tempting to add some labels to all of the time series that it exposes that tell you what the role of that thing is, like some metadata information, like the role of a machine in this case, and just add that to all the exposed time series directly from the target. The problem is if that role or other metadata information changes over time, then this breaks all the time series, meaning when the value changes, all the time series coming from this instance will transition to a completely new set of time series. And if you're doing any over time operations on these time series, they all kind of reset and you have not an ideal situation. So try to keep either those, try to break those extra non-identifying but informational labels into one separate metric that is exposed from that target. That you can then join in whenever you actually need it during a query. Again, some details in this blog post here. For alerting now, there's again some good general guidelines. Many of you might know this document by Rob Evershook, written a long time ago. He was at Google once, wrote a philosophy on alerting. It's quite a long Google doc. When you go on it, you always see a lot of anonymous animals at the top reading it. But some of the main takeaways are, try to page on user visible symptoms, like, hey, is the site down? Is the site slow? Are there errors? Versus trying to page an on-call person on all the possible underlying causes of a failure. Because there's too much underlying noise and you're just going to overload the on-call person. There's some exceptions, of course. If the site is still working well, but you can already detect that the disk, for example, will be full in 4 hours, you probably want to alert on that. Generally err on the side of fewer pages to not overload an on-call person, because then they will just start ignoring pages. And still track the causal metrics to then help you debug when you do get paged. But try to not alert too much on things like load average, CPU usage, memory usage, and so on, right? Getting more Prometheus specific again. So consider this alert here, where we are we want to alert when a service that handles HTTP requests encounters too many errors. So we have an error rate, we have an error counter for our job. We take the rate and we say, okay, if the rate per second is over 10, please alert me. That actually works, but what happens if Prometheus cannot actually scrape that service, the job equals my job, at all? Then these errors total time series will not be present at all. So the entire expression actually ends up being empty again. Same if Prometheus isn't even trying to scrape them, because for some reason, either your job name is misconfigured or the service discovery is broken, not returning any targets or so on. Again, you're not getting any results for this alert. It will silently fail and not tell you that something might actually be wrong. So it's a good idea for all the services, the jobs in Prometheus that you actually care about, to have at least 2 types of upness and presence alerts here. So the first one, acting on the up metric of the Prometheus server, that the Prometheus server automatically records for every target scrape. It's 0 if the scrape failed, 1 if the scrape succeeded. This will tell you basically, whenever Prometheus has an issue scraping your targets. And you can have different variants of this. You can either really alert on any individual target that cannot be scraped. You could also have an average over all your ups of one job to tell you if too many of them cannot be scraped and so on. But have some alert on the up metric. And then in the second case, where Prometheus isn't even trying to scrape the job that you think it should be trying to scrape, you can use the absent PromQL function to tell you if the up metric isn't even being recorded because no scrapes are happening for that job. And the absent function will return 1 time series if the input is empty. So that allows you to detect that situation. The alerting definitions in Prometheus, the alerting rules, allow you to specify a duration for which a condition needs to be in a bad state before an alert actually gets sent to a human, when it goes from pending to actual firing. And it's good to specify that for duration. So imagine you have a very simple alerting rule here: alert me for any down instance that cannot be scraped, like this. And you don't have any for duration. It defaults to 0. So the first evaluation of this alerting rule will immediately already cause an alert to be sent to a human when there's one single failed scrape, some network blip and whatever. And those can always happen easily. And you want to be somewhat robust in the face of very temporary glitches. So I recommend having at least a couple of minutes of a for duration for all your alerting rules to be robust against these temporary blips. Same in this example here. Imagine you're alerting on the absentness of the up metric, but you are starting a completely new Prometheus server, which hasn't gotten a chance yet to actually scrape any targets. Then for the very first couple of seconds, this might also immediately alert you, because the up time series is not present yet for that job. So again, add 5 minutes, or a couple of minutes at least, until you're sure that some data has been scraped for that up metric. So in general, I would say make this at least 5 minutes. Also in alerting rules, a lot of people want to alert on the overall behavior of a system. So they use, for example, the sum aggregator to aggregate over a whole bunch of time series to get a total rate of something, and then say like, hey, if this error rate is too large, please alert me. But then they don't put any modifier after the sum modifier, the sum aggregator, to keep some of the labels. And labels are your friend in Prometheus. They go all the way from instrumentation to your actual alert manager in the end, that then routes alerts and aggregates them based on all those labels. So try to think of if there are actually any labels that you may want to preserve, that you don't want to aggregate away, especially the common ones that are all the same between all those time series anyway. For example, the job is kind of the service that all these metrics are coming from. And that is a very prominent label that you may want to actually route on in the alert manager later on. So you could have a by job in there to preserve the job label and preserve possibly other common labels, but the job label is one of the most important ones. Even better, you could, instead of using the by modifier to the aggregator, you could use the without modifier, which is an exclude list approach, where you really just specify the labels you do not want to keep. So then automatically you get to keep all the other ones. Okay, some querying tips. A metric name, again, is just an opaque string to Prometheus, and different services can actually theoretically use the same metric name with totally different meanings and send it to Prometheus. And especially you have a shared Prometheus server, and then you are querying just by a metric name. You're not 100% sure whether maybe you're really just selecting metrics from your service or also from some other team's service that has named their metrics in exactly the same way. The only kind of namespace you have in which you know that a metric name has exactly one meaning is typically the binary that it is coming from. That's the job in Prometheus. The job is a group of processes that are all the same binary with a similar configuration, usually replicated web services or so. So I would recommend always having some scoping in your selectors in addition to the metric name, just to make sure that you're really only selecting the time series that you are expecting. There's certain functions in Prometheus that work properly only on counter metrics and not on gauge metrics. So again, counter metrics are metrics that track cumulative totals that normally can only go up, but sometimes reset when the process that counts those events or whatever they are restarts, then it starts again at 0. A gauge metric, in contrast, can naturally go up or down. Memory usage going up or down, disk usage going up or down. But there's functions like rate, irate, increase that tell you how fast a counter is actually currently going up. And these counter-specific functions look at the underlying samples of the time window you pass into them and see if any sample value decreases from one sample to the next, and then they assume, oh, it's a counter metric, so this has to be a counter reset. So I assume that this counter actually has restarted since 0, and it kind of tries to hide that fact, and will only ever return you a positive or at least 0 rate. So if you put disk usage in there, you want to see how fast my disk usage is going down. This will never happen. It will always think that whenever that disk usage is going down, that it's a counter reset, will only give you a positive value. It's going to give you a nonsensical value, but it's not going to tell you. So that's dangerous. Because, again, there's not that typing being fully plumbed through yet to the TSDB and into PromQL, like letting that function know, like, hey, you're actually operating on the wrong type of metric. So you have to watch out for this as a human. These 4 functions here, they are reset aware. That can only happen with counters. So you have to be careful to only use them with counter type metrics. And vice versa, there's other functions, deriv and predict linear, which actually do not have this concept of trying to detect counter resets. For example, the deriv function just does a linear regression to tell you how fast per second a time series is going up or down. So this can actually return negative results. So if you put a counter metric in there, then it will give you the wrong result as well. When a counter metric resets, it will actually think, yeah, you are actually getting a negative number of resets of requests right now. So you have to be careful as a human, again, to not switch these around. Also, the rate function and some other functions that compute rates of increase need at least 2 data points under the provided time window to be able to calculate such a rate. Otherwise, they will just return an empty result for the respective time series if they just find 1 sample. And so you want to make sure that that rate window is large enough to always robustly select at least 2 samples. And you can always have a brief bad scrape, or even be a bit unlucky with the actual rate window alignment compared to the underlying physical samples. So to be really robust against those situations, I would recommend having at least 4 times your scrape interval as the actual window that you're using. So if you're scraping every 15 seconds, for example, use a rate window of at least 1 minute to be robust. Last point here, monitoring topology. About how do you plug in different parts of your monitoring. I actually only have one major point here, which is a thing we see often. There's a temptation for people to build one large exporter that pre-aggregates a lot of data from a lot of different systems and services and hosts, and then Prometheus only pulls once from that centralized big Uber exporter, so to say. Whereas you could also have this other model where you really have very fine-grained exporters as targets that Prometheus can pull individually. So let's have just a look at these and what the different problems here might be. So imagine you have, in this case, a per-machine exporter, right? You have this one big pre-aggregating thing on each host, and all the different applications on that host send their metrics to it. Whether it's locally push or pull, doesn't really matter. You have a web application in there, you have a MySQL server, you have host metrics, container metrics, all the different things. It's awesome, right? You can just push all those metrics into that exporter, and then Prometheus can be really simply configured. Prometheus now only needs to scrape a single exporter target. Is that great? Well, only on first glance. It clashes a bit with the way that Prometheus wants to monitor things. So, first of all, it might become an operational bottleneck if different teams now have to talk about, how to store and namespace their metrics in that one exporter. It can become a single point of failure with little isolation between the different metrics in there. Also, as a Prometheus operator, you may want to only scrape certain types of metrics, right? You may want to have one Prometheus server that only has database metrics and not all of the random other stuff that's on that host. Also, normally when Prometheus pulls from an individual target, it records this up metric that I talked about earlier that tells you whether a scrape succeeded or not. So normally you can base upness monitoring on that already. And here this becomes harder because you're only doing one huge, humongous scrape with one target. So it becomes harder to know, of all the different metrics from all the different things that are in there, which of these things are actually healthy in terms of just being there and reachable. Also, if you are using some kind of really awesome service discovery mechanism, like you would be using on Kubernetes, those service discovery mechanism gives you a lot of cool labels for all the different targets that you're discovering. A different pod, for example, would have the name of the pod and maybe the namespace and different other things that then get automatically added to all the time series that are scraped from those targets. So it's now harder to actually, for Prometheus to automatically slap on the correct metadata that it has discovered to all these already existing metrics that are all jumbled together in this one big box. So if we go to this one exporter per process model, all this becomes a bit more Promethean. So this is what I would recommend. Really have very fine granular scrape endpoints that Prometheus can go to individually. For the actual own applications that you write yourself, just use a client library, put metrics directly in there, serve a Prometheus metrics endpoint that Prometheus can pull from. And for the existing other things that Prometheus cannot directly pull from, put a single process or single host or single whatever thing exporter next to it, as long as it looks like one target to Prometheus. Then you can make use of all these awesome things. Like the Prometheus server admin can now decide which metrics they actually want to scrape in that specific Prometheus server. And all the upness metrics, you can now make really detailed use of them, and all the juicy metadata is automatically associated with all the individual scrapes. A similar thing is, some people try to abuse a component in the Prometheus ecosystem called the Pushgateway, which also allows for very limited batch job use cases to hold on to some metrics and then let Prometheus scrape them from the Pushgateway, and it can be abused in a similar way. Like, don't try to use the Pushgateway as kind of an intermediary thing for totally normal services. Just writing everything in there to transform Prometheus into a push-based monitoring system, because then you run again into pretty much all of these same issues and some more. And the some more issues are again outlined on here. All right, that's already it for today, and thank you very much.
Yeah.